All right, let's jump right in. Imagine you're standing on a street corner in a city that's a perfect grid. Your destination is several blocks away, and the rules are simple. You can only walk south or east. So, how many different ways can you get there? Today, we're going to crack this classic puzzle, a real favorite in coding interviews known as the unique paths problem. Let's get to it. So here's the setup. You're at the top left corner, and you need to get to the bottom right. The only moves you can make are right or down. That's it. No going backwards, no cutting through diagonally. The question is, how many completely unique paths can you possibly take? And believe it or not, this simple little question leads to some really elegant solutions. This puzzle is actually the perfect gateway into a super powerful technique called dynamic programming, or DP for short. Specifically, we'll be using what's called 2D DP. We're going to break this whole thing down and solve it from the ground up, literally building our answer right on top of the grid itself. So what is dynamic programming, really? Think of it like this. Instead of tackling one giant, scary problem head-on, you break it down into tiny, manageable pieces. You solve each of these little subproblems just one time, and this is the key, you save the answer. Then you just use those saved answers to build up to the final solution. It's all about working smart, not hard. Okay, so how do we apply that DP mindset here? Well, instead of getting overwhelmed trying to count every single path from the start, let's flip the question. For every single square on the grid, let's ask, how many ways can I get to this specific spot? If we can solve that for every square, one by one, we'll eventually have the answer for our final destination. And the logic here is actually super intuitive once you see it. Think about the top edge. To get to any of those squares, you have to come from the left, right? There's only one way. Just keep moving right. So every spot on the top row gets a 1. Same for the first column. You can only move down, so they all get a 1. Now, for any other square in the middle, how could you have possibly gotten there? Well, you had to have come from either the square directly above it or the one to its left. That's it. So the total number of paths to a cell is just the paths from the top plus the paths from the left. And what we've just discovered can be boiled down to this neat little formula, which is called a recurrence relation. This right here, this is the engine of our whole DP solution. It's just the fancy mathematical way of saying what we already figured out. The number of paths to get to any spot is just the paths from above plus the paths from the left. Okay, so we've got a working solution. Awesome. But if you're in an interview, you know the next question is always going to be, can you make it better? And by better, they usually mean, can you use less memory? And in this case, the answer is a big yes. See that first approach we did? It needed a whole m by n grid to store all our intermediate answers. But think about it. When you're calculating the paths for a new row, do you really need the entire grid? Nope. You only need the answers from the row right above it. This little insight lets us use something called a rolling array. We just keep one single array and update it as we go down. This is a huge win. We go from needing m times n space down to just, well, the width of the grid. But hold on. What if I told you we could solve this whole thing without building any tables at all? There's this incredibly cool mathematical shortcut that comes from a field called combinatorics, which is basically the art of clever counting. Let's just think about this in a totally different way. To get from start to finish on an m by n grid, you have to make a certain number of moves down, m minus 1 of them to be exact, and you have to make n minus 1 moves to the right. Every single valid path, no matter how zigzaggy, is made up of that exact same number of down and right moves. So the problem isn't about the grid anymore. It's about counting how many unique ways you can arrange that sequence of moves. And it turns out there's a specific tool for this in math. It's called a binomial coefficient. All this fancy notation means is, out of a total number of moves, which is m plus n minus 2, how many ways can we choose which ones will be the down moves? This single formula gives us the answer directly. No loops, no tables. It's insanely fast and uses practically zero memory. Pretty cool, right? Okay, that math formula is beautiful, it's elegant, but it's also a little fragile because what happens when the interviewer throws you a curveball? What if some of the squares are blocked? Suddenly, you've got roadblocks you can't go through. And this is the crucial part. That elegant little formula we loved so much, it completely falls apart. It just assumes you can go anywhere, so it has absolutely no idea how to handle a blocked path. It can't subtract the routes that are now impossible. But guess what doesn't break? Our original dynamic programming approach. It's way more robust. We only have to make one tiny little tweak. As we're filling out our grid,
if we get to a square with an obstacle, we just say the number of paths to get there is 0. That's it. Our top plus left logic automatically takes care of the rest, making sure that blockage correctly influences all the other path counts.
All right, so we've looked at this from a few different angles. Let's pull it all together into a simple playbook for you so you know exactly which tool to grab from your toolkit depending on the situation you face in an interview.
So here's the breakdown. The standard 2D-DP is your reliable starting point. It's easy to explain, it's logical, and most importantly, it handles obstacles. Then you've got the 1D optimized version. This is your upgrade. It does everything the first one does, but with way less memory, which is a huge plus. And the math shortcut? Oh, it's the superstar for speed and memory, but remember its weakness. It only works on a perfectly clear board.
And last but not least, let's talk about the traps. The things interviewers are waiting to see if you'll fall for. The absolute biggest one is trying to use the math formula when they've added obstacles. Other common mistakes are getting your numbers wrong by 1, forgetting to set up your 1s on the edges of the grid, or trying to solve it with basic recursion, which will just time out. Knowing these pitfalls is half the battle. So there you have it. We've totally cracked the grid problem. We know the core DP logic, we know the super fast shortcut, and we know exactly when each one is the right tool for the job. But I'll leave you with this little brain teaser to think about. How would everything change if you could also move diagonally? What would that new DP formula look like? Figuring that out is the perfect next step.